All right, today we are shrinking down, way, way down, to explore a hidden dance that's happening literally everywhere, all the time. We're going to dive into the invisible world of spinning molecules.
I mean, think about that for a second. How on earth do you measure something that's a billion times smaller than a grain of sand? It sounds completely impossible. You can't just, grab a tiny ruler. But it turns out scientists have this incredibly clever way of doing it. And it all comes down to watching these molecules spin. So here's our game plan. First, we'll look at why molecules are always moving. Then we'll use a simple model to make sense of it all. After that, we'll dive into the strange quantum rules they have to follow, figure out how we can actually read their spin, and finally, see what these incredible molecular fingerprints tell us about, well, everything. Okay, first things first. Molecules are not static little dots. They are never truly still. They're constantly in this energetic dance, vibrating, zipping around, and for our purposes today, they are constantly rotating. Just imagine them as countless tiny energetic tops, spinning away endlessly. So, how do we study this invisible spinning? We use a technique called rotational spectroscopy. And the basic idea is actually pretty straightforward. We essentially zap molecules with microwaves, and then we watch how they respond. It's kind of like a super precise radar gun for the quantum world. Now, you might be thinking, wait, real molecules are way more complicated than that. And you're absolutely right. They stretch, they bend, it can get messy. So to make any sense of it, scientists start with this brilliant simplification called the rigid rotator model. Let's break that down. The model is just beautiful in its simplicity. We basically pretend that a simple molecule, one with two atoms, is just a tiny dumbbell. The two atoms are the weights on each end, and that chemical bond between them, that's just a perfectly rigid, weightless little rod. It sounds simple, but this picture is so powerful for understanding the physics of how things spin. And what's really important here is that not all of these little dumbbells spin the same way. The resistance to being spun is called the moment of inertia. Think about a figure skater. When they pull their arms in, they spin way faster, right? It's the same idea. A molecule's spin depends on how its mass is spread out. If you have heavier atoms or a longer bond, the moment of inertia is higher, and it's harder to get that molecule spinning. Okay, so we've got our spinning dumbbell. But here's where things get really, really interesting and a little weird, because when you get this small, the normal rules of physics kind of go out the window. Now we have to play by the strange and very strict rules of quantum mechanics. You see, a spinning top in our world can spin at any speed and just gradually slow down. But a molecule? Nope. It can't spin at just any random speed. Its energy is quantized. This means it can only exist in very specific, allowed energy states, with absolutely nothing in between. It's like having a car that can only go exactly 10 or 20 or 30 miles per hour, but never ever 18 or 25. The best way to visualize these allowed energy states is to think of them as rungs on a ladder. Each rung has a label, a quantum number we call J. So the very bottom rung, J equals 0, that's the ground state, no rotation at all. To start spinning, the molecule has to absorb just the right amount of energy to jump up to the next rung, J equals 1, and then to J equals 2, and so on up the ladder. It has to be on a rung, it can't hover in between. So we have this quantum ladder of energy, but how on earth can we actually see a molecule climbing it? This is where those microwaves we talked about earlier come back into the picture. It's a great question, right? The molecule can't just decide to jump. It needs a very specific little push of energy to make it from one rung to the next. So what gives it that push? That push comes from a photon of microwave radiation. When a microwave with the perfect amount of energy, the exact difference between two rungs, hits the molecule absorbs it and uses that energy to hop up to the next level. If the energy is a little too much or a little too little, the microwave just passes right by. It has to be a perfect match. Okay, this leads to another really important point. Let's say a molecule is at the bottom of the ladder. If it gets hit with a really high energy photon, can it just leap all the way to the top in one go? Well, the quantum world has some very strict opinions on that. These are called selection rules, and they are not optional. For this kind of spectroscopy, the rule is super simple and super strict. A molecule can only jump one rung at a time. The change in that quantum number J has to be exactly +1. So jumping from J equals 1 to J equals 2, that's allowed.
But jumping from j equals 1 all the way to j equals 3? Forbidden. It's a step-by-step climb. No skipping rungs. Okay, so let's put it all together. Molecules absorb very specific microwaves to climb a quantum ladder, one rung at a time. This is where it all pays off. By seeing exactly which microwaves get absorbed, we get an absolute treasure trove of information.
And here's the magic. If we shine a whole range of microwaves through a gas and just keep track of which frequencies get absorbed, we see this distinct pattern of lines emerge. And because every single type of molecule has its own unique moment of inertia, its own unique ladder spacing, this pattern is a perfect fingerprint. It lets us identify that molecule with absolute certainty.
And why is that a big deal? Well, this fingerprint is unbelievably powerful. By analyzing it, we can work backward to figure out the molecule's exact moment of inertia. And from that, we can calculate the precise distance between its atoms, the bond length, with incredible accuracy. We use this to identify molecules in those giant gas clouds between stars, or even to analyze the chemical makeup of atmospheres on other planets. It all really boils down to this one simple but totally profound idea. Just by watching the way a molecule spins, we can measure its fundamental shape and its size. We can decode its very identity from light years away. So a simple spin can tell us so much about a molecule's structure, but rotation is just one part of that constant molecular dance. So it leaves us with one last question to chew on. If just spinning reveals all of this, what other secrets could we unlock if we could also measure the way molecules stretch and bend? But that's a story for another time.